Hi there, it's Mr. Baker with another physics video. It's another exciting one. I'd like you to see if you can guess the lesson. You got it? Well, yeah. OBS. Big Bang. So we're looking at the Big Bang today, and we're going to be answering this question: how old is the universe? So let's first of all then look at how the universe has evolved. This is a really quick flyby of the life and the future of the universe. The universe begins 13.8 billion years ago with an event known as the Big Bang. Both time and space are created in this event. After a fraction of a second, rapid expansion occurs during a billionth of a billionth of a billionth of a billionth of a second. The universe is the size of a grapefruit. After 100 to 1,000 seconds, nuclei of hydrogen, helium, lithium and other light elements are formed. After a few 100 million years, matter clumps together under its own gravity, forming the first proto-galaxies and with them the first stars. Initially, the expansion of the universe decelerated, but a few billion years after the Big Bang, the expansion begins to accelerate. The acceleration is caused by a mysterious force known as dark energy. After 9 billion years, the Sun, along with its 8 planets and all the asteroids, comets and Kuiper Belt objects, such as Pluto, form from the debris left behind by the earlier generations of stars. After 10 billion years, the first life appears on Earth in the form of simple cells. We're now 13.7 to 13.8 billion years on. Using our own ingenuity, humanity is probing the depths of the universe and trying to unravel its mysteries. After many, many years in the future, stars will no longer form, matter will be trapped in black holes, protons will decay and black holes will evaporate. Let's now explain some of the evidence that's helped us shape the ideas about the universe. Edwin Hubble was born in 1889 and he died in 1953. He was an American astronomer who played a crucial role in establishing the field of extragalactic astronomy and is generally regarded as the leading observational cosmologist of the 20th century. He measured the redshift of distant galaxies and found that the galaxies are moving away from us. Henrietta Leavitt was born in 1868. She was an American astronomer who discovered a way of using the periodic changing of brightness of some stars to accurately measure the distances between galaxies. She died in 1921. Without her discovery, Hubble would not have been able to go on to make the conclusions that he did. So, if all of the galaxies are moving away from us, does this mean that we have a special place in the universe? Do we have to be at the centre? Well, no. Everything is moving away from everything else. So if we were on another galaxy, we would observe exactly the same things. There were two competing theories after looking at Hubble's evidence: the Big Bang and the steady state theory. The Big Bang theory's proponents were Einstein, Hubble and Lemaitre, and they thought that the universe was expanding after exploding suddenly in a big bang from a very small point, which we now call the singularity. They thought that space, time and matter were created in the Big Bang. Now this was a theory that was brand new, and Sir Fred Hoyle, a Yorkshire astronomer, and most other scientists thought that the universe is infinite and unchanging. Possibly matter is entering the universe through white holes and pushing the galaxies apart, and this was why the galaxies were moving further apart. But then in 1965 a satellite called COBE measured this. This is a picture from a satellite facing away from the Earth towards the universe. It's not a picture of stars and galaxies, they've been taken out of the picture. It's a picture of what's left over. It's a picture of the background microwaves that are leftover traces of the gamma rays that were produced in the Big Bang. On May the 20th, 1964, American radio astronomers Robert Wilson and Arno Penzias discovered the cosmic microwave background radiation, the ancient light that began saturating the universe 380,000 years after its creation. And they did so pretty much by accident. Robert Wilson is an American astronomer born in 1936. Arno Penzias is also an American physicist and radio astronomer, and he was born in 1933. Bell Lab's Holmdel horn antenna in New Jersey picked up an odd buzzing sound that came from all parts of the sky at all times. The noise puzzled Wilson and Penzias, who did their best to eliminate all possible sources of interference, even removing some pigeons that were nesting in the antenna. When they'd gotten rid of every possibility, they realised they'd discovered something big. They'd spotted the CMBR, the predicted thermal echo of the universe's explosive birth. the landmark find put the Big Bang Theory on solid ground, suggesting that the cosmos did indeed grow from a tiny seed, a single point, about 13.8 billion years ago. So, there are two main pieces of evidence for the Big Bang. Redshift. Nearly all galaxies are redshifted, meaning that they are moving away from us. This means two things. The universe is expanding, and as it is currently expanding, if we wound back time, the universe would get smaller and smaller until we got to one single point, the singularity. And two, the CMBR, the cosmic microwave background radiation. We don't expect there to be many microwaves all around us in the universe. The reason there is cosmic microwave background radiation. It's the radiation that's been stretched out over time because the universe is expanding. Again, if we wound back time, then this radiation would become a wave with a much smaller wavelength, gamma rays, which we would expect to be made just after the Big Bang. So, in the Big Bang Theory then, we start off with this singularity, this single point where the entire universe, matter and time are all situated. There's a Big Bang, and then everything else is stretched out. So the galaxies are moving further apart from each other, and the waves that were first produced, the gamma waves in the Big Bang, are stretched out to become microwaves that we can observe now. When we think of an explosion, we might think of a bomb exploding into the air. The Big Bang Theory isn't quite like that. All of the matter was already in that single point, and all that's been happening over the last 13.8 billion years is that matter, that time, that space has been stretched out. And you can model this idea with a balloon. If you stick some stars onto a balloon and then draw some waves on it, as you blow the balloon up, the stars, acting as though they're the galaxies, will move further and further apart, and the waves will get stretched out. So what's the future for our universe then? Well, there are two main theories of what might happen. The Big Crunch, and this is where the universe will reach some point and then all of a sudden go back in on itself. Or the Big Yawn, it will carry on forever and ever. So what do scientists think? For many years, scientists have tried to work out the density of the universe. The answer to this would give them an idea of whether the universe is going to expand forever, or if the gravitational attraction between all of the objects will eventually slow to a stop, attracting everything back together in a big crunch. Since 1998, astronomical observations of supernovae have suggested that distant galaxies are moving away increasingly faster. The expansion of the universe appears to be accelerating. Scientists don't entirely understand how this could happen, but they've come up with an idea called dark energy. Another recently discovered anomaly is that galaxies seem to rotate too quickly for the mass of their stars. This suggests that there is a mass of the universe that is invisible to the instruments used by scientists. Scientists only know that it is there because it has gravity that affects nearby objects. This unknown material has been called dark matter. Astronomers have calculated that 27% of the universe must be made of this dark matter. If dark energy continues to dominate, the most likely outcome is the more dismal one. The current expansion will continue forever, gaining speed so that all the galaxies we now observe, 100 billion of them or so, will one day disappear beyond our ability to detect them. Our galaxy will be alone in the visible universe, and then once the stars burn out, the universe will be truly cold, dark, and empty. And that is the end of our lesson, on a very miserable, depressing note there. So that has been our lesson on the Big Bang, and these are the things you should be able to do. You should be able to state the currently accepted model of the early universe and describe the evidence that backs up this model. You should be able to describe why scientists were initially reluctant to accept the Big Bang model. You should be able to describe the origin of the CMBR and how it supports the Big Bang Theory, describe the changes in the universe from the time of the Big Bang to the present day, and outline recent discoveries that have led to changes in the theories of how the universe will develop. So we asked at the beginning, how old is the universe? So using Hubble's law, we can find the age of the universe to be about 14.5 billion years. When the cosmic microwave background radiation is factored in, we get a more accurate age of just under 13.8 billion years. Okay, so that's been our lesson on Big Bang Theory. I've been Mr. Baker, this has been another physics video, and I'll see you next time. Thanks very much.